Hello everyone, I'm Professor Londoño. Welcome. Today, we're diving into a really cool classic physics mystery. The question is this: how could you possibly measure the speed of a bullet if all you had was a block of wood and some string? Sounds impossible, right? Well, we're going to look at the amazing device that was built to do just that.
Okay, so let's set the scene. I want you to imagine it's way back in the 19th century. There are no high-speed cameras, no fancy electronic timers, nothing like that. So what do you do if you need to know how fast something is moving? Like, say, a cannonball. Yeah, that's a real problem, and that's the exact puzzle the ballistic pendulum was invented to solve.
So, before we even touch the pendulum, we need to do something every good scientist does. We need a baseline. We've got to figure out the projectile's speed using a totally different method first. That way, we have something to compare our pendulum results to. And we're going to do it with just a tape measure and, well, good old gravity.
All right, so here's what we do. The setup is actually pretty simple. We take the pendulum out of the wave for a minute and we just fire the ball horizontally. That's it. As it's flying forward, gravity is of course pulling it down. All we have to do is measure two things. The height it started from, we'll call that h, and the horizontal distance it traveled before it hit the floor. We'll call that d.
And the physics behind this is it's really elegant. You see, because gravity's pull is constant, the amount of time the ball is in the air only depends on how high up it started, that h value. So we can calculate that time pretty easily. And once we know the time, and we've already measured the distance d, well, speed is just distance over time. Boom! That gives us our target value, the real speed, which we'll call v1.
Okay, baseline established. Now let's bring in the star of the show, the pendulum itself. But hold on, before we can use it, we have to get to know it a little better. We've got to understand its properties. Think of us as detectives gathering clues. We need to measure all its vital statistics before the main event happens.
So what are these clues? We need to lock down three key things. First up, its mass. Easy enough, we'll call that m. Next, we need its center of mass, r. That's basically its perfect balance point. And finally, we need to measure its period. That's just the time it takes to do one full swing back and forth. That little measurement is going to let us calculate something really important called its moment of inertia.
So, moment of inertia. What in the world is that? Well, the easiest way to think about it is like rotational mass. It's a measure of how much an object resists being spun. An object with a high moment of inertia is, well, it's stubborn. It's really hard to get it rotating. And once it is rotating, it's just as hard to stop. And believe me, this stubbornness is a super important clue for our mystery.
And you know, finding that center of mass, r, isn't some crazy, complicated math problem. Nope, it's a hands-on measurement. You literally just take the pendulum and you try to balance it on something sharp, like a knife's edge. And that one single point where it rests perfectly without tipping over, that's it. That's your center of mass.
All right, we've got our baseline speed. We've gathered all our clues about the pendulum. It is time for the main event. We put everything back together and we fire the projectile straight into the pendulum's basket. For just a split second, that ball and the pendulum become one single thing, a unified system.
Now, the really crucial thing here, and this is super important, is that the collision happens incredibly fast. I mean, the ball hits and gets embedded in that basket almost instantly. And it's because it's so fast that we get to use some really powerful laws of physics.
And here's the first big tool that helps us crack this case. Because the collision happens in the blink of an eye, we can basically assume that no outside forces, like friction or air resistance, have time to mess things up. And that means the total amount of spin in the system, what we call angular momentum, is conserved. In other words, whatever angular momentum the system had right before the impact, it has the exact same amount right after.
Okay, so now all the pieces are on the table. We've got everything we need. By using two absolutely fundamental principles. First, the conservation of angular momentum during that instant of collision. And second, the conservation of energy during the swing that follows, we can actually work our way backward and figure out that projectile's initial speed.
Let's unpack this a bit. So before the collision, on the left side here, all of the angular momentum is coming from that little ball moving super fast. Makes sense. Then, after the collision, on the right side, that very same amount of momentum is now shared across the whole combined system, the pendulum and the ball stuck inside it. They're now rotating together at a new, slower speed that we'll call omega 2. And since we know before has to equal after, we've just created a perfect mathematical link between the bullet's original speed, v1, and the system speed right after the hit, omega 2.
But that leads to a pretty obvious question, right? This whole collision is over in a flash. There's no way we can actually see or measure that speed right after the impact. So how in the world do we find out what omega-2 is?
Well, here's the clever part. The answer isn't in the collision itself. It's in what happens right after. We don't need a fancy camera. We just have to watch. We just need to see how high the pendulum swings. That maximum height, we'll call it a capital H, that single measurement is the key that unlocks this entire mystery.
Okay, take a look at this. This shows us what the energy looks like the very instant after the collision. The pendulum is at the very bottom of its swing, which means it's moving at its absolute fastest. At this point, pretty much 100% of its energy is kinetic energy. That's the energy of motion.
But watch what happens. As the pendulum swings upward, it starts to slow down. It's trading its speed for height. And when it gets to the very peak of its swing, it actually stops for just a tiny fraction of a second. And at that exact moment, look, all of that kinetic energy it started with has been transformed into potential energy. That's the energy that's stored up just because of its height.
And that's it. That's the final piece of the puzzle. Because of the law of conservation of energy, we know the energy at the top of the swing has to equal the energy it had at the bottom. So just by measuring that height, h, we can calculate the potential energy at the top, which tells us exactly what the kinetic energy was at the bottom. From that kinetic energy, we figure out omega-2, the speed right after the crash. Then we take that number, plug it back into our first equation for angular momentum, and out pops v1, the original speed of the projectile. How cool is that? Mystery solved.
Now, this whole thing is way more than just a clever classroom experiment. It's really elegant for sure, but the principles we used here, conserving momentum and conserving energy, these are absolutely fundamental to how we understand and, more importantly, how we engineer the entire world around us.
And you've probably felt this in real life without even realizing it. Think about being on a playground swing. If your friend just tosses you a tennis ball, not much happens. But what if they throw you a big, heavy medicine ball? Wham! The impact is going to send you swinging way higher. It's the exact same principle. You and the swing are the pendulum, the ball is the projectile. Its momentum gets transferred to you, and all that new kinetic energy gets turned into the potential energy of a much higher swing.
And seriously, once you start looking for them, you see these principles everywhere. Forensic scientists use them to reconstruct what happened at crime scenes based on bullet impacts. Aerospace engineers rely on them to calculate how to dock spacecraft together without, breaking them. And even the car you ride in, the crumple zones are designed specifically to absorb the energy of a collision, keeping you safe. It all comes back to momentum and energy.
Now, I gotta be honest. If you do this experiment in a real lab, you'll find that your calculated speed is a little bit off. It'll seem like some energy just vanished. But it didn't. This is because the collision isn't perfectly bouncy. We call it an inelastic collision. That missing energy was actually converted into other things, like the sound of the impact or the heat that was generated when the ball squished into the basket. The energy is still there, it just changed its form.
And that really brings us to a final pretty cool thought. This incredibly simple tool from the 1800s shows us one of the most profound truths in physics. Energy is never created or destroyed. It just changes form. And it makes you wonder, right? Think about the heat coming off your laptop right now, or the sound your car makes. Where else in our daily lives are these hidden energy transformations happening all around us, all the time, without us even noticing?